February 15th, 2013, in the peaceful morning sky of Chelyabinsk, Russia, a giant object came from space. It did not carry the light of hope, but a space rock heavier than the Eiffel Tower, passing through the Earth's atmosphere at a speed of more than 60,000 kilometers per hour. At an altitude of 30 kilometers above the ground, it exploded. An explosion brighter than the sun, but strangely silent. For 90 seconds, no one heard anything. Only a blinding light tore through the frozen sky. Then suddenly, the shock wave came. The terrible sound resounded. Windows exploded. Glass flew like rain. More than 1,500 people were injured just because they stood by the window to watch the most beautiful phenomenon of their lives. The shock wave was so strong that it destroyed thousands of buildings. And that tragedy, ironically, occurred on the same day that scientists correctly predicted another asteroid would pass by Earth. Just 16 hours later, the Duende asteroid, which was about the same size, flew by a mere 27,000 kilometers from Earth, closer than the orbit of a geostationary satellite. They saw Duende, but did not detect the giant rock that was hurtling toward Russia. And most frightening of all, this is not uncommon. Since 1988, more than 1,200 asteroids larger than 1 meter have hit Earth. Of those, we only detected exactly 5 before they hit, and never with more than a day to prepare. With all our modern technology, with hundreds of telescopes on the ground and in space, why is humanity still helpless against stray rocks from space? What are the chances that a giant asteroid could actually destroy most, if not all, life on Earth? And if that day comes, what can we do? Asteroids, it sounds simple, but they're ancient fragments left over from the dawn of the solar system. For 0.5 billion years ago, dust and rocks swirled around the sun, condensing into molten spheres. These were protoplanets. Heavy metals like iron, nickel, iridium sank to the core, while lighter silicates formed the crust. Some protoplanets grew into the planets we know today, typically Mercury, Venus, Earth, Mars. But many others collided, broke apart, creating billions of small pieces, which continue to float in space. These are asteroids. Basically, this object is the remaining core of a small planet, formed 4.5 billion years ago. When it was young, the inside was molten, heavy metals sank to form the core, while lighter materials floated to the surface. Then, in a violent collision with another asteroid, it broke apart, and the fragment, now just a cold hunk of iron, is the oldest witness humans have ever seen. Most asteroids have a stable orbit between Mars and Jupiter in the main asteroid belt. But some wander away from their safe zone, drifting towards Earth. These are called near-Earth objects, and they're the greatest threat humanity faces. In his last book, Stephen Hawking warned, "Asteroid impacts are the greatest danger to life on Earth." However, detecting them is extremely difficult. Most asteroids are observed with ground-based telescopes. Astronomers have to take a series of consecutive pictures, 1, 2, 3, 4, and compare them, finding a small but moving among the still stars. That bright spot is an asteroid quietly orbiting the Sun. But it is not easy to recognize it. These objects are not large, just a few meters or a few kilometers, and in the endless sea of space, they're almost invisible. Even small asteroids can be catastrophic. The Chelyabinsk asteroid, for example, was only about 20 meters wide, about the width of 2 school buses, but still created an explosion 30 times more powerful than the Hiroshima atomic bomb. The reason they are so hard to spot is because they are so dark. Their rough surfaces, which absorb most of the light, reflect only about 15% of the sunlight that falls on them. So they are best seen when the asteroid is at a 45-degree angle to the Sun, where the light hits its surface directly. This phenomenon is called the opposition effect, and it means there could be countless more dangerous asteroids floating around us, hidden in the bright sun, where no telescope can see them. Chelyabinsk is a prime example. The asteroid approached from the Sun, leaving all monitoring systems on Earth completely blind. To date, humanity has discovered and cataloged more than 1 million asteroids in the solar system. Most of them are in the belt between Mars and Jupiter, but 24,000 of them are near-Earth objects. And it is these dark wanderers that we need to keep an eye on every minute. Detecting an asteroid is hard enough. Determining whether it will hit Earth is even harder. Imagine you're watching a small dot of light moving slowly among millions of stars. You have only a few days of data, a vague trajectory, and from those numbers you have to predict its position in tens, even hundreds of years. It's like trying to predict the trajectory of a bullet in flight, just by looking at its trajectory in the first split second. Any error, no matter how small, will magnify over time, making the path appear hazy like a shadow floating in space. Even if we had perfect data, there would still be a natural limit, the boundary of predictability. Asteroids don't simply orbit the Sun in a stable orbit. They're constantly being pulled, pushed, and influenced by the gravity of giant planets like Jupiter, Venus, and even Earth. Each time they pass a planet, a slight tug from gravity is enough to change their orbit forever. And that's dynamic chaos, a phenomenon that, after a certain period of time, no one can say exactly where that asteroid will end up. And in fact, The maximum human prediction threshold today is only about 100 years. Beyond that limit, nothing can be guaranteed. That makes collision prevention a race against time. Because if a meteorite really hits, the consequences will be terrible beyond imagination. In the middle of the arid desert of Arizona, there exists a giant wound on the surface of the Earth, the Barringer crater. A scar more than 170 meters deep, nearly 1.2 kilometers wide. Formed by the collision of an iron meteorite about 50,000 years ago. The first person to believe that this place was the remnant of a meteorite collision was Daniel Barringer, an American mining engineer. At the beginning of the 20th century, most geologists thought this was just an ancient volcanic crater. But Barringer did not believe so. He believed that a giant metal meteorite had crashed into this land. And deep under the hard rock was a treasure of pure iron, worth more than $1 billion at that time. Driven by ambition and belief, in 1903, Barringer planted mining stakes and began drilling to the bottom of the crater. He believed that if he dug deep enough, the giant metal meteorite would appear. But he was wrong. He drilled down hundreds of meters, then drilled horizontally, drilled around the cliff, looking for any trace of iron. Year after year, decade after decade, he found nothing. Someone said, maybe the meteorite didn't fall straight, but diagonally from the west. And so he drilled in another direction. If you go to Barringer today, those drill marks are still on the cliff like wounds of faith. What Barringer didn't know was that the meteorite he was looking for never existed. When a giant object hits the Earth at 30 kilometers per second, the energy released is equivalent to a giant atomic bomb. The extreme temperature and pressure at the moment of impact vaporized the entire meteorite, turning it into superheated metal gas, spreading throughout the atmosphere. The explosion obliterated the impactor, the object Barringer had spent his life searching for. For 27 years, he drilled more than 400 meters into the Earth, persistently like a sleepwalker searching for the past. But the object he was looking for had evaporated tens of thousands of years ago, leaving only a deep wound. The 50-meter asteroid, not much larger than Chelyabinsk, released the energy equivalent of 10 megatons of TNT. That's more than 600 times the energy of the Hiroshima bomb. So the closest thing to a meteorite impact is a massive nuclear explosion. This is the actual size of a T-Rex skull. As for how dinosaurs were wiped out in the past, here's the answer. About 66 million years ago, at the end of the Cretaceous period, Earth was a world teeming with life. Dense rainforests stretched across the planet. Giant dinosaurs ruled both land and sea. In the sky, pterosaurs with wingspans of more than 10 meters glided over warm coastal regions. None of them could have known that, in just a few minutes, their entire era would end. Somewhere in space, an asteroid about 10 to 12 kilometers in diameter, weighing billions of tons, was hurtling toward Earth at a speed of more than 20 kilometers per second. At the moment of impact, the energy released was equivalent to 100 million megatons of TNT, billions of times the explosive power of the atomic bomb dropped on Hiroshima. The impact site was the Yucatan Peninsula, Mexico today. There, the meteorite fragment penetrated the atmosphere, crashed straight into the shallow sea, and created a giant crater more than 180 kilometers in diameter. This crater was later named Chicxulub, after a village near the center of the crater. The temperature at the point of impact increased to thousands of degrees Celsius. Rocks and seawater evaporated in an instant, thrown into the stratosphere. A tsunami more than 300 meters high spread across the oceans. Molten rocks were thrown into the air and fell like rain of fire, setting all the forests on Earth on fire. Within hours, the planet was in flames. And over the next few days, ash, sulfur, and steam filled the atmosphere, blocking out sunlight. Global temperatures plummeted. Photosynthesis stopped. The food chain collapsed. So, aside from the initial explosion near the actual impact site, the first effect of this impact was that the sky became a massive heat source, and it roasted everything on the ground. So, basically, these creatures were roasted while they were still walking. The only animals that stood a chance were those that lived in underground tunnels or possibly underwater. And they could have come back and colonized the Earth without the dinosaurs as a major obstacle. Over 75% of the Earth's species disappeared, including all non-avian dinosaurs, nearly all giant sea creatures, and countless plant species. This was the KPEG mass extinction, one of the largest biological events in the planet's history. The remnants of the impact are still there. After being buried for tens of millions of years under layers of sediment, the Chicxulub crater was discovered by scientists in the 1990s. Inside, they found a thin layer of soil containing iridium, an element rare on Earth but common in meteorites, evidence that the Great Extinction event began in space. What are the chances of Earth being hit by another asteroid 10 kilometers in diameter or larger? In your lifetime, Assuming you live to be 100, you will have an impact every 100 million years of a 10 kilometers asteroid, like the KT Extinction event. So the chance of this happening in a year is 1 in 100 million. Statistically, the chance of being wiped out by a 10-kilometer asteroid in your lifetime is almost negligible, essentially zero, because current surveys show that no object that large will collide with Earth in the next 100 years or so. Long-term efforts by the scientific community have pushed the probability of a global catastrophe to extremely low levels. That is the good news. But if we zoom out, the picture changes rapidly. The proportions and sizes of asteroids are exponential. For every 10 kilometers asteroid, there are about 1,000 that are 1 kilometer in diameter, and the number gradually increases as the size decreases. 1 to 2 kilometers asteroids are no longer enough to wipe out all life on the planet, but they're still enough to wipe out a territory equivalent to a large country. Imagine France or Germany disappearing under a meteorite strike. Fortunately, we have found most of the 1 to 2 kilometers asteroids. Sky survey programs estimate that they have detected about 90%. Some even say the figure could be as high as 98%, meaning that in terms of risk at this level, we are currently in a relatively safe state. The real danger lurks in the middle layer, asteroids of several hundred meters. A rock of several hundred meters in diameter is powerful enough to wipe out a large city. It does terrible damage. It destroys buildings, blows up infrastructure, starts fires that spread across the region, and if it hits the ground, the debris is launched and falls hundreds of kilometers away, causing disaster. The problem is, there are still too many objects at a range of a few hundred meters for us to detect. We are missing a significant portion of this group. And here is the most chilling thing. Such a devastating impact could happen tomorrow. Not a common scenario, but theoretically possible. There are rocks big enough to destroy cities, and we have not cataloged them all. So when the warning appears, if an inevitable explosion is imminent, what options do humans have? There have been many meetings, scientific committees, and hypotheses about emergency response, among which one solution is often proposed: destroy or disintegrate the asteroid with an explosion. The idea sounds intuitive. If you can't steer it in another direction, then break it into smaller pieces. But the reality is much more complicated. Bombing a celestial body does not eliminate the danger. It may break the object into many pieces, but the pieces still carry a lot of energy, and they may spread out, not disperse quickly enough to avoid causing damage. The impact of an explosion on or under the surface of a celestial body, the fragmentation, the change in orbit depends on too many parameters: size, composition, porosity, velocity, angle of impact, making the outcome very difficult to predict. In short, we have almost eliminated the risk of global catastrophe within our knowledge, but the serious regional threat from rocks of a few hundred meters still exists. And at present, if an emergency alarm sounds, our options for action are very limited, and the consequences of proactive measures, such as bombing, remain an open and risky question. Even if we were to force the space object to pieces, gravity would not be ignored, it would pull the pieces back together. The result would be a loose mass of matter, a reformed rubble pile. And if the object was not a rubble pile to begin with, it may have become one after countless collisions in the past. So the idea of blowing an asteroid and thinking the problem is solved is a big mystery. We don't yet understand enough about how the fragments will disperse, rotate, and reconverge. A gentler option is to attach a motor to the surface and then gently nudge the orbit. The idea sounds simple: nudge slowly, enough to deflect the trajectory until it passes safely. But when you calculate the actual numbers, it's not that simple. It takes a lot of force, and to generate that force, the rocket has to stick to the surface, which we don't yet know how to do reliably on a rotating, possibly hollow, or rubble-like rock. Forget about blowing up the asteroid, and forget about just trying to stick a rocket to it, because the real-world description has its harsh limits. Some have suggested using lasers to boil the rock and create a jet, but we don't have powerful enough lasers on Earth, and the idea of deploying a laser network in space is still on the border between science fiction and futuristic technology. There are even more outlandish ideas, like wrapping the asteroid in aluminum foil to change its reflectivity, using solar radiation to gradually change its orbit. It's an interesting idea, but the reality is we don't have the capacity to launch enough material, and we don't yet know how to do it on that scale. Frankly, at present, there is no reliable technology that would allow us to deflect a kilometer-sized asteroid. Such an asteroid is powerful enough to wipe out a country. For a 10-kilometer asteroid, any attempt becomes 1,000 times more hopeless. We have come up with countless creative solutions, but when weighed against physical reality, most of them prove impossible. So what can we do now? Let's go back to the most basic and most practical thing. Prevention begins with detection. If the expected impact location is known in advance, the most reasonable option may be to evacuate the affected area. But even evacuation has its limits. A large city has millions of people, limited transportation infrastructure, and history shows that mass evacuation in a short time is an extremely difficult task. Highways are blocked, vehicles break down, and millions of people may not be able to leave in time. So the most sensible answer is, do what is within our reach now. Invest in sky surveys, build advanced telescopes, deploy sensors in space. The sooner we detect them, the more time we have to calculate and focus resources on the most dangerous objects. Once a particular object is identified as a threat, the entire scientific and engineering community can rally, test orbit-altering strategies, and prepare the most sensible civil response options. If you're worried about asteroid impact, doomsday scenarios, here's what you need to know. We have eliminated most of the biggest global risks thanks to survey programs. But regional threats, especially from objects a few hundred meters across, are still there and need to be addressed. The most effective action right now is not a heroic, risky strategy, but rather increased detection, monitoring, and preparedness. Thank you for listening. Please subscribe to our channel to get the latest news about our galaxy.